Okay, so in your last lesson, you learned about pressure of gases. In this lesson, we are going to talk about temperature. So we are most familiar with the Celsius scale. Also, did you know it was also known as the centigrade scale? And this was developed by a Swedish scientist named Anders Celsius. Centigrade means centi, means 100. Grade means degrees, so it means divided into 100 degrees. And it is convenient for most everyday situations, but a most useful temperature scale was developed by Lord Kelvin, and this was called the Kelvin scale. So the Kelvin scale starts at 0 Kelvin, and we call this absolute zero. What is absolute zero? Maybe you've heard of this before. It is the theoretical temperature at which the entities of a material contain no kinetic energy, therefore transmit no thermal energy. So we know that temperature is a measure of kinetic energy. So at absolute zero, there is no movement at all. And this temperature in degrees Celsius is minus 273.15. So a little bit more about the Kelvin temperature scale. We also call it the absolute temperature scale, and it begins at 0 degrees Kelvin, and we use the symbol K. There are no degree signs for Kelvin, and there are also no negative values. So this makes it most useful for the gas law calculations, and all of your temperatures must be in Kelvin to do these problems. It's imperative that you change it or you will get an incorrect answer, and you sometimes have to convert it back to degrees Celsius. So how do we do the conversion? So the conversion is capital T, and that represents Kelvin, is equal to lowercase t, and that would be your Celsius, plus 273. So let's try an example. So an example would be, convert the following temperature from degrees Celsius to absolute temperature. Dry ice sublimes into a gas at negative 78 degrees Celsius. So write down what we're given. Our Celsius temperature is minus 78, and we want to put it into Kelvin. So uppercase T is equal to lowercase t plus 273. And that would be minus 78 plus 273. Put that in your calculator. I've done it right here, and you get 195 Kelvin. Therefore, minus 78 degrees Celsius is 195 Kelvin. Okay? So today we're going to look at the first gas law, and the first gas law we're going to look at is Charles' law. So in Charles' law, volume and temperature of a gas are directly proportional. That means, so we would use this symbol, directly proportional. V, that means as volume changes, temperature changes. And the relationship between the volume of gases and the temperature was developed by Jacques Charles, and this is why it's called Charles' law. So I'm going to flip that over. So Charles determined that the volume of a gas increases as its temperature increases proportionally, provided that the pressure, the amount of gas, remains constant. So the law states that as the temperature of a gas is increased, the volume of a gas increases, provided that the pressure and the amount of gas, the number of moles, okay, so that would be the amount. That's our amount, not just, an amount in everyday terms. can be, I have a dozen eggs, that's an amount. But when we talk amount in chemistry, we mean moles. And this remains constant. The volume and temperature of a gas are directly proportional. So mathematically, we can represent Charles' law by this equation. V is equal to, this is alpha times T, which is a constant. Okay? So if we rearrange the equation, the constant is equal to V over T. So we can apply this to any two sets of volume and temperature values. This is the formula that we're most concerned with here. This up here is just telling how we get to that, okay? Now this only applies when temperature is measured in Kelvin, so it's extremely important that you note that. Okay, I know you've got to write that down. So you must change your temperature into kelvins. And what's imperative here is that you get the correct variable with the correct number, or you will mess up the answers. So just be very careful when you do this. Okay, so let's take a look at this says example 2, but this is our first example of this type of question. So a balloon is filled with 2.50 liters of dry helium at 23.5 degrees Celsius. That's a condition. The balloon is placed in a freezer overnight. When the balloon was removed, the volume was found to be 2.15. What is the temperature in degrees Celsius of the freezer if the pressure remained constant? So what are we given? We have a V1 is equal to 2.50 liters. And our temperature, T1, is equal to 23.5 degrees Celsius. Okay, so we put that into Kelvin. We just learned how to do that. We add 273. We can just do that in this space right now. Minus 23.5 plus 273. And we get 249.5. That doesn't really make sense. Oh, because it's not minus, that's why. It's not a minus. So this is 23.5 plus 273. That's 296.5. We didn't really need our calculator for that, but why not? So that's just Kelvin. Remember, there's no degrees for that. 296.5. I'm just going to fix that with 6 there. Okay. Make sure this is in the right spot. Okay, so, and our second volume is 2.15 liters. So V2, 2.15 liters. And we're trying to find T2. So V1 over T1 is equal to V2 over T2. We're solving for T2. So whatever way you want to solve it, if you want to solve for this in terms of T2, you can rearrange. You really should get good at this, right? So T2's on the bottom. I would put T2 on the top, on both sides, right? What you do to one side, you have to do the other. So that means this cancels out, right? Then I'll just rewrite this in the next line so we can see it line by line. So we're left with that. So we now want to isolate T2. So we have to multiply both sides by T1. Okay? So that means these cancel out, right? So I'll take it step by step again. So I'll just rewrite this line. Some of you this might be easy for you, but others need to still work at it, which is fine, but you should get good at it. It's kind of fun to do, actually. I enjoy doing this kind of thing, rearranging. So we want to get T2 alone now, so we have to then what? It's attached by multiplying, so divide by V1. Right? So that means those go away. And there we go. So that's our rearranged equation. Now, of course, however you get to it is fine, but that's how you rearrange the equation. So then we substitute our numbers in. Make sure you get the right one. So V2 is 2.15 liters. Our T1 is 296.5 Kelvin. Divide by V1, 2.50 liters. Good. And And before we actually put this calculation through our calculator, let's think it through. What are we going to expect to see happen here? What have we done to our volume? We had 2.5, we're going to 2.15. So we know that our volume and temperature are directly proportional. So what are we expecting to see happen to our temperature? Yes, of course, it's also going to go down. That's what we should see. So when we go through all of our work, if we see that that's not the case, then we've reasoned that we've done something wrong, right? So keep that in mind when you're solving these problems. Okay, so let's put this in our calculator. I still had the other number in there. Times 2.15 equals divided by 2.5. And I get 255 Kelvin. Why can I use 255? Well, everything here has 3 digits, right? So 255 Kelvin, so I can do that. But I need to go back to degrees Celsius. So how am I going to do that? Well, because I'm adding to go from Celsius to Kelvin, I'm going to subtract 273, right? So minus 273 negative 18. Negative 18. I just didn't leave much room for my little negative mark there. Equals negative 18. And of course I need 3 digits, so 0.0 degrees Celsius. So did it go down? It sure did. So we did this correctly. And of course we need a therefore statement. The temperature of the freezer would be negative 18.0 degrees Celsius. Okay, so that's pretty much how all these problems work. So a couple more points on this. As the temperature of a gas increases, the kinetic energy of the gas entities also increases. The entities move more quickly, and the number of collisions between the entities increases. And the number of collisions between the entities and the walls of the container also increases, making the container expand, increasing the volume of the gas. So what are some applications of this? Well, one would be a pop-up turkey thermometer, if you ever use one of those in your turkey, because as the temperature increases and the turkey cooks, the air in the thermometer expands to pop up that little plunger, okay? And that's calibrated to a correct internal temperature. So now you know, that's Charles' law. Also, if you've ever taken a helium balloon outside from inside, you'll notice it crumbles. Bring it back inside, then it expands again. Okay, this is because the gas takes up more space when it warms up, right? Kinetic energy, that's what temperature is a measure of. Oh, this is a fun fact for your ping pong balls. If you guys play ping pong, if you've ever dented it, you don't have to throw it out. You just take a pan of water, put your ping pong in there, warm it up gently, and pop, it's gonna expand for you, okay? Oh, and one last thing, because we're getting into warmer weather, your tire pressure. You must check it at a cold temperature, right? Charles' law, right? Because if you measure at a colder temperature, if a warmer temperature, the tires are gonna have expanded already, so you won't get a proper measure. Okay, so there are some fun facts that apply to Charles' law. So there's some questions for you to try here at the bottom. Try as many as you like. The solutions will be there for you. Okay? Have a great day. Ask any questions. We're available for you. Bye.